isn't it? So basically the building blocks are flip-flops, right? And the flip-flops, whatever control inputs are there, like set, clear, then clock, everything has a role in making up of a register, isn't it? So in the initial level of a sequential circuit, we have studied about flip-flop. Then in the next level, we have made the flip-flops as a group. So in that group only we have studied the counters, then registers in the last class. Okay, so in the registers, again, if at all I have to elaborate more, there is one specific register which is having universal operations. Like we can say it is a universal shift register. Right. Now what is the beauty of this? A universal shift register. So I'll start from register side. Register, it can in fact store the data. Okay, it can in fact store the data. Just a second. So sorry. In class, man. मेरा class में class मेरा 10:50 को just start हुआ है. बस students का. Means मैं ना class में. ठीक है. I'm so sorry. Basically, I'm so sorry. I just don't want to attend some meeting. That's why I'm telling them. Okay. Right. So sorry. Right. So now registers. Right. So register is used for storing the information. Yeah. So we have already group of flip-flops there. Now shift, which is able to perform the operation of transfer, isn't it? Now what is universal shift? I can break to shift register. It can shift from right to left register or left to right register. So that is from shift register. That is the work of a shift register. Now what is universal? Now universal means they have some specific qualities, like it has the capability to parallelly load and parallelly input, parallel output, have a shift right and shift left at a time. Okay, that means we can have some controls there. Another thing is we can deliver the data at the same time retain the data, just like last class we have seen about the shift. So can we develop such a universal register? That is what it is. Now universal shift register is a register which, you guys are there?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay.
Yes,
So
ma'am.
universal shift register is nothing but a small shift register only, but with extra benefits. That's all. Okay, now how we are going to design that? Designing doesn't require much task. It is only the combinational circuits which will append the main registers are nothing but the options. Now just a second, I'm trying to ask. Right, I want controls like shift right. Okay, then shift left. Right, so these two I have to perform. Now just we will think hard. Right, can I use shift right operation and shift left operation? For example, I have two flip-flops. Oh, I will not tell like that. Sorry, not in terms of flip-flops. I will tell in terms of blocks. That might be easy. This is there. Okay, this is A, this is B. Okay, so now this is register A and this is register B. Inside that they have two flip-flops. Consider it is having two flip-flops. Okay, they are all with some clock or something. We can put all those extra fittings. Okay, now I have to transfer from A to B, right? And I also have to transfer from B to A at a time. Means one at a time. So for to be performed, can I have some control linked? Means control means what? I have to design a small combinational circuit which can help me out. Like at this hour, shift right is performed. At this point, shift left is performed. Are you able to get what design I am trying to probe you? Like see, I have some values like shift right means what? This side, right? So all the A has to be transferred to B. So that has to be performed when some input is given. Which input will to be given? Okay, anyway, I'll give the output. I'll give the solution itself. Can I use a multiplexer which can control this?
Yes, ma'am. 2x1 mux.
Yeah, we can use the multiplexer. Why? Because see, when I was delivering itself, I was trying to tell controlling. That control thing can come only from a multiplexer, if at all I'm not wrong. And moreover, I'm giving the clues, we can use some combinational circuits, isn't it? So a multiplexer is best suitable for that. In fact, in the universal shift resistor, they have used a multiplexer only. Other than that, not much. Nothing, no other decoder is not preferable. In fact, encoder is also not preferable. These are all not preferable. Multiplexer has the best option. Why? Because it has single output. So anytime one control happens, like shift right should happen at one stroke. Shift left should happen at one stroke. Okay, parallel loading can happen at one stroke. Right? And then parallel outputs can be generated. Then this is what the attributes of universal, isn't it? Universal shift resistor, as such, it is already designed. We need to analyze only the circuit. Just a second, I'll try to share one small information on that. Yes. Right. Now, can you see the slide?
Yes, ma'am.
Yes.
Yeah. So now, a universal shift resistor, yes, a universal shift resistor has what? A clear control, a clock input, okay, shift right, and shift left operation, and apart from that we have a serial input lines and output lines associated with that. Okay, so these are the qualities of the universal shift resistor which I was mentioning. Okay, just go through the points. You will definitely have a clear. Why? Because we are using flip-flops. We will have definitely a clock pulse because flip-flops do have what? Clock, right? And that will it is in the synchronized mode because we will use more than one flip-flop. Similarly, you will have shift right operations and shift left also to be performed. Right? Now, just a second. I will now try to tell another one. Parallel load control, then parallel output line. These are all something. Okay, I will not try to explain anything here. Now I'll just show a diagram. Okay, what is this thing? We will try to analyze. That's much easy. Before reading what is the universal shift resistor, I am showing the universal shift resistor block diagram itself. Right. So from the block diagram we can analyze easily. Now just see here. There is four. I will start from the top. Just check out. There are 4 D flip-flops, isn't it? Just check on the screen. There are 4 D flip-flops. All are synchronized. From there only you take. 4 D flip-flops, all are synchronized with the clock. Isn't it? Is that noticeable? Right? Now, yes, the output of the D flip-flops are considered as the final outputs. Right? Prior to the D flip-flops, there is a small circuit made up of multiplexer. Now, those are very beautifully connected. Just check out. The 4 multiplexers are having a value. What is that? It is a 2 cross 1 I should say, or 4 cross 1 I should say. 4 by 1 mux, right? Isn't it? What is the mux size? Yes. 4 cross 1? Yes. So definitely you will have 2 select lines, isn't it? Now, according to the connection and according to the constraints on the universal shift resistor, I have serial right, serial left. So 2 operations already done. Third operation, it has to be parallelly loaded. Third one is also done. Then fourth one is what? We have to keep the values also unchanged. So I can have 4 conditions satisfied with those flip-flops by using a multiplexer, isn't it? Can you just check out there? Right now, check out the conditions there happening. Now, multiplexer 1, 2, 3, 4, all are parallelly connected, isn't it? Parallelly connected to the 4 D flip-flops. Right now, this design is not a rocket science, it's very easy. So 4 D flip-flops are there already. Okay, then afterwards we have 4 multiplexers. These are all D. 4 is to 1. 4 is to 1. 4 is to 1. Okay, now 4 is to 1 means definitely we will have 4 input lines. They have 2 control lines. So the control lines I can say S0, S1, I think they have select lines we will call S0, S1, and then they will be anyway common. 4 inputs, 4 inputs, 4 inputs. Okay, so this S0, S1 we can connect common and need not show because it looks clumsy. This S0, S1 is common to all the multiplexers. Okay, now S0, S1 controls every value. What is that? First thing, I can make a table like this. What operations to be performed? Okay, so if I give 0, 0 here, all the 0 lines will be selected. 0, 1, 2, 3, 0, 1, 2, 3, isn't it? 0, 1, 2, 3, or you can say I0, I1, I2, I3. You remember that, right? Right. So now 0, 0 means all the zeros are selected. Yes or not? All the zeros will be selected. Hello? You guys are there?
Yes, ma'am. Yes, ma'am.
Yeah. So all the zeros will be selected. Now, according to this diagram, okay, we did not first we will analyze this, afterwards we can have our own design. 0 is connected. All the zeros of the mux you check what it is doing. It is having a what? Interconnection from here to here, isn't it? Like what? It is unchanged. That means whatever output is there is again fed back or fed input. We can tell like this, isn't it? This is our Q, no? So whatever is output is there, that will be selected. Now carefully understand this S0, S1 is going to all. So I cannot draw line into this one. So consider S0, S1 means zeros of everything is selected. Now according to the circuit diagram, what is happening? Yes, what is happening? The output is interconnected, isn't it? When the 0 is selected, there is a feedback connected. A3 is coming back, then afterwards A2, A1 is 1. So what does it mean? Hello?
Output will not change.
Yes, that is what? No, 0, 0, there is no change according to this particular diagram. Okay, that means the output remains the same because we are using especially D flip-flops. So they have used A3, A2, A1, A0. Okay, consider that. So no change. Right? Now, when S0, S1 is 0, 1. Okay, that means all ones will be selected. So what 1 is doing, how the 1 is connected in the every multiplexer? Serial input for shift right. That means what is happening? What is happening? This 1 is selected. So that means all the ones are selected. So here the input will be provided. Serial input for shift right operations has been. Then afterwards what will happen? If this 1 is selected, what is that happening? This particular 0 is connected to 1, isn't it? Did you see here? Did you see there? What is happening there? The 0 is connected to this, then 1 is, that 0 is connected to the next one, that 0 is connected to the next one, isn't it? Have you checked the lines? We have to do the
Yes,
shifting.
ma'am.
Yes. So that means this 0 will go to this one. Okay. So this 0 will have with 1 and this 0 will have with 1. So shift right operation will always be performed, will automatically be performed because 1 is selected here. All the ones are selected and see the connections, how the ones are connected there. Isn't it? Please try to understand. See, serial input for shift right will be provided at the first mux. Okay, so first mux will be getting the first input, right? Then afterwards, this 0 is connected to the first one. That means previous one will be shifted this side. Then the 0 of the means the previous one, old one is there, it will shift next, isn't it? Is the shift right is happening?
Yes, ma'am.
Is it happening or not?
Ma'am,
Yes,
Yeah,
happening.
happening?
ma'am,
Okay. Now somebody has doubt. Yeah, please. Tell.
ma'am,
Somebody's asked.
why zeros of one mux is connected to the one for the next mux?
Why?
Means
Because I want to have, see, when the shift right has to happen, according to the theory, what is there? This one, it has to go like this, no? I told, right? The first one will get the fresh input. The old one will move to this. Old one will move to this. Old one will move to this. In order to happen that, the fresh is coming to the first one, right? Old is already with the 0. So that is connected to 1. Because
okay.
old is already there, no?
Yes, ma'am.
So the old one will be shifted. The old one, like that, it will be shifted. Got it? That's why
Yes, ma'am.
0 is connected. Now go to the next one. 1 0 is there. Shift left operation is done. So 1 0 means what? 2 should be selected. Now 2 should be selected means what? Here shift left serial input for left. The fresh input is provided here. Now how the connection should be? Don't check there. Check it here and there. What should be connected? Fresh input is coming this side, no? 2. Then
One should be connected to the next two.
1 should be connected to the,
Two of next mux.
okay, then what? Then how it should? Shift left one. Just check the shift left has to perform. The fresh one is here. Okay, the fresh one is with 2. Right? Now from this one it has to come this side. So how it would be? The old one has to come now.
Ma'am, output of previous one will be connected to 2.
That is what. So from where it has to come? Which side? Output switch from where it has to come? A0, A1, A2, A3?
Yes, ma'am, from A0, A1, A2.
See, shift right and shift left operation. Please try to understand. Shift right operation is being performed. Why? Because serial input is here and already this is loaded already. So that interconnection is easy. But shift left, what is this? Here we will input this side, this side, this side should come. So that means if the fresh input is loaded here, this old one has to come this side. This old one has to come this side. Isn't it? Yes or no? Then only now we will get the left. So that is what happening there. So if the fresh one is in this point, okay, so old one of A1 or old one of A0 has to go to 2 of this, isn't it? Old one of this has to go to 2.
2.
Right? Then old one of A1 has to go to this. Then old one of A2 has to go to this. Then old one of A3, we don't have anything, so no connection. Right? Because this is fixed. Please try to understand. Whereas in the shift right, why this old one, see, there also I can tell the same thing. Fresh one is here, right? This particular one has to go to this particular one. That also you can draw. No, but it looks clumsy, that's all. Okay, this one has to go to this one. This one has to go to this one, isn't it? That is shift right. Shift left is the one what I have drawn. Okay, that is given in short. Please try to understand. Shift right means what? Fresh one will go to this one. Okay, the old one there has to connect to the next one. The old one of this has to connect to this next one. The old one of this has to connect to this one. That only is shown. Please try to analyze. Is that correct? Is that fine? Only thing is you will get multiple lines there to show. Just show with arrows, no issue. The connections, multiple connections.
Ma'am, in the slide for
Yeah.
0 1, the circuits are given for 0 1 select lines.
0 1 select lines means what? No? Oh, 0 1 is
Means
S0, S1 is interchange.
means for right shift the circuit is given in the slide.
So what?
I am confirming that.
You are referring that. Yeah, go ahead, please. Who is talking? Whoever is talking, please go ahead.
Ma'am, I was just confirming that, means.
Oh, you're confirming that. Okay, right. So now, see, here the number of lines are made very short. If at all you want to open up, this many lines will be shown. See, shift right, you have given for 0, 1. Shift left, you have given for 1, 0. Now 1, 1. Another option is there. Selecting of 3, 1, 1. What happened? You can check there are fresh inputs there. Ready? I0, I1, I2, I3. Fresh inputs will be into the multiplexer. So that only will be going. Now, why I am telling you this story? Why? Because since I have so many constraints to the same register, I am trying to tell that each control can have one operation. Isn't it? Now, shift right, shift left. That there only I think most of the people will be getting confused. Shift right and shift left is nothing but, see, whatever the information is there, first information has to go to the last multiplexer. Shift right means from the old one you connect it to here, from the old one. All the ones are enabled. That time, whatever the connections are there, that only will be doing, isn't it? So that is
Yes,
how they are managed. Yes, that is how they are managed. Now, if we can check out this particular part, what is happening? For 0, 0, there is no change. For 0, 1, there is a shift right performed. For 1, 0, there is a shift left, and 1, 1 is a parallel loop. Right? So now, this is one of the universal resistor. We can design our own also. Can't we give 1, 0 for shift left? 0, 1 for shift left, and can we interchange 0, 0 unchanged? We can change all those things, right? Isn't it? The controls are with us. How the connections will be changed, isn't it? Wait a minute. I wanted to do 0, 0 for parallel load. Okay. Then 0, 1 for shift left. 1, 0 for shift right. And 1, 1 for unchanged. How the circuit will change? Right? How the circuit is going to change?
Now we will connect the output lines of
Yeah,
flip-flops
that's
for
at max
or
what will
1
happen
1 to the input lines.
yeah, at max what will happen? Only the connections will be changed, isn't it? Anything new will happen, we will do that easy. So we have 4 flip-flops. 4 B flip-flops. Right? All are synchronized. All this is the your outputs are ready. Okay, so this is A3, this is A2, this is A1, this is A2. Okay, now I have this multiplexer, same multiplexers I will use, and then in short we can prepare 0, 1, 2, 3, 0, 1, 2, 3. In fact, you can put I0, I1, I2, I3, no issues. The select lines as small as 1. They are also interconnected, showing this is 4:1 mux, and the 4:1 mux, 4:1. These all lines, they are interconnected. This arrow shows that they are all interconnected. Okay, it is going to D. This is going to D. Okay, now what is happening? 0, 0 parallel load. So what I will do? I will keep here inputs, fresh inputs. I am giving the notation. This is the highest MSC. Can I do that? When 0, 0 control is there, parallelly all zeros, whatever 0 is selected, that will be performed. Is that correct? Yes or not?
Yes,
Yes,
ma'am.
ma'am.
So 0, 1, shift left. That means my shift left operation has to start from this to this, my left. Okay, mine. Right. So I will give serial input for shift left here. Right. Now, this one is there. Means select lines is having 0, 1. All the ones will be selected. So whatever the connections are there, that only will be performed. So if the fresh one is here, that means the old one of this has to go to this one, isn't it? Right? Whatever it is, old one, whatever is available, that has to come. Right? And this one has to go to this particular one, because that is what it is showing. Because this table is more important. This is what the operation to be done, isn't it? And now this particular one, we don't know where to go because this is end. Dead end. Is that fine? Shift left. Right. Now shift right. That means I should perform this side. So shift right, all the twos will be selected. So this is serial input for shift right. So now shift right is from this to this. This one has to go, whatever old one is there, it has to go to 2. This one has to go to 2. This particular one, it has to go to 2. Right? And that one has to go to the next. I don't have anything. Right? Now, 1, 1, unchanged. That means all the threes will be selected. Whatever is there, it has to be retained. It has to retain. Now you can see this is a good combination of a sequential and a combinational together. Very well used. Is that clear? If this is decided, the connections are with you. You need not mug up that, isn't it? Yes or not?
Yes, ma'am.
Yes, ma'am.
Easy or not? So this is what a universal shift resistor. Now I will ask you one question. Can we add some more new things to this? Like other than these, can we add some more new? New like what? You may question. Hello? Like what we can yeah. Any new ideas you are getting, like new things we can add, means in the sense like can I change instead of a multiplexer something else here? See, multiplexer is best suited. I am asking for the alternative. Yes, this question is for everybody. Please do participate. Yes. What happened?
D flip-flop is taking one input, so how other than multiplexer will be suitable?
Can you repeat, ma? Who is telling?
Ma'am, D flip-flop is taking only one input.
Yeah.
So how other than multiplexer will be suitable?
Okay. So to make it much more clear, you are telling that since D flip-flop is only taking one input, isn't it? You want me to use any other flip-flop there instead of D flip-flop? Who is asking this question? Never mind. Is it you?
Yes, ma'am.
Yeah. What's your question? Please come again.
Yeah, ma'am. You were asking that except multiplexer, we will use other.
No, any other combinational circuit is preferable, or any other combinational circuit here is preferable other than multiplexer. Any other combinational circuit. No? Because it's already shown, so every time it will steer, the brain will steer only to multiplexer, isn't it? Okay, so another one. Think that if I don't have a D flip-flop, but other than D flip-flop, register means it is mandatory there should be D. We cannot do any changes there, isn't it? So forget that. D flip-flops cannot be changed. It has to be there. Only option is other than multiplexer, what else we can do? We can use AND and OR gates, no problem. Doesn't matter. Isn't it? AND OR gates combination can be used.
Yes, ma'am.
Okay. So we can use AND OR combination instead of multiplexers. That also is possible because multiplexer if you open, in fact it is also AND and OR combinations only. Right. So this is the one of the established register which we will call it as universal, but definitely not very universal. Why? Because it is at max performing 4 operations at a time, like with different commands. Right. Now, apart from this, after this universal shift register, there was a small information, or maybe in elaborate version, these registers are having some applications or some link with the counters. Now, counters is already a finished version for us, isn't it? We have done synchronous and asynchronous counters. Yes or not? Yes or not? We have done synchronous and
Yes,
asynchronous,
ma'am.
and in fact we have done more counters also. But now I will try to point out some of the facts which are going inside the counters, and especially a decade counter. Okay, now for a decade counter we normally go from 0 to 9, isn't it? Now just check. Right, I'm showing you up. Okay, am I moving, am I going correct? Up counter, just an example. Afterwards I'll explain why I have done this. Is that correct? 0 till 9, then afterwards 0 back. Isn't it? It's enough? Yes or no? Right, we are not bothered about the circuit. Yes, you guys are there? Oh, I'll stop.
Yes, ma'am.
Yes. Okay. Right, now hold. So now, if you observe, if a change is there from 1 to 0, carefully understand. If a change is there in the previous state from 1 to 0, then only a change is happening in the next bit. Statement you please try to understand. If there is a change from 1 to 0, right, then only a change is probably entering into the next one. I'll explain you what is this. Right, now just see here in the last bit, it changed from 0 to 1. This bit as it is, it has come. This bit as it is, it has come. This bit as it is, it has come. This is observation, only observation. Now, check here. This is first state. State, I'm talking state. This is second state. This is third state. Now, in the third state, from second to third state, if it is moving, 1 to 0 it has come. So, immediately there is a change here also. A ripple has come here. That means 1 to 0 change has created a change in the next bit. Right? In the next bit, if you see 0 to 1 change has happened. As usual, the next one, nothing has happened. Nothing change has happened. This is as it is, this is as it is. But this one, a ripple came. This is introduced a ripple. Right? Just observation. Right? Now again, 0 to 1. No change here, no change here, no change here. 1 to 0, a ripple came. It changed to 1 to 0. A ripple came, 0 to 1. Then this is as it is. So, what is my observation? Whenever there is a change from 1 to 0, right, from previous state to this one, next bit of the present state is getting a ripple. Like it is also getting changed. Did you observe that? Is it happening everywhere? Just check. Just check that. This is exclusively in decade counter. Exclusively we can see. Is that fine? Our observation is fine?
Yes, ma'am.
Isn't it?
Yes, ma'am.
Right. So now this specific observation has created, okay, another small set of counters called ripple counters. Now you can ask such type of decade counters even we have done as a synchronous also. In the synchronous mode also we have done a decade counter. In the asynchronous also we can do a decade counter. But this is observation which is specifically telling that use a negative clock pulse, right? Negative clock pulse one, connect the output of the first one to the next one, right? Asynchronous, especially asynchronous. Don't you think the ripple can be passed? Yes or no? Exclusively here only. Whenever you see the 0, 0, same as it is, nothing. 1, 0, there's a ripple. 0, 1, as it is, as it is. 0, 1, as it is, as it is, as it is. 1, 0, that 1, 0, 1, 0. Ripples are coming whenever ones are zeros are there. 0, 1, as it is, as it is, as it is. 1, 0, oh, 1 to 0. Here, no change, no change. This one. This change. How I should stop, by the way?
By
You have
clearing.
observed in the last. Yes, yes, yes.
By clear input.
Clear, ma'am.
You will clear it. Yes. So you have to, after that, we have to clear it. So now, did you see? So from here only we have done a mod counter, isn't it? Mod counter. Afterwards, clear means again we will have a fresh load, isn't it? You remember that?
Yes.
Yeah. So this is what.
Yes, ma'am.
Another, yeah. This is what another observation they are trying to tell in this. Just a second. In this particular one, I will try to tell you. So this observation has actually steered a new circuit called a ripple counter, which a brief description is also provided, which we have already done. So now just check out. So ripple counters, if at all you can see here, this one. I was trying to explain that only. So now, if at all you go, this is how a basically ripple state diagram will be exclusively for decade counters. It will go. And just check out. Is this circuit what we have designed is the same one? Like you can check out Q1, Q2, Q4 and Q8. That means 8421 code. According to the weights we have been provided. Have I read this? Is this doing the same?
Ma'am, the circuit for ripple counter seems somewhat like of asynchronous also.
Yeah, ripple counter is an asynchronous counter only actually. Only thing is they are trying to specifically tell here that this asynchronous counter mostly it works from 1 to 0 change, and if you see it's a negative edge clock pulse. That's why the small sect has been elevated, because this observation earlier we have not seen, right? Okay, similarly they have proposed so many counters. I'll just show you. So many counters. This is just a proposition. In fact, this is also generation of sequences only, but this is a different proposition. Okay, they have observed this. Right. Now, if at all you see another one. Right. This is another specific one. Listen. If at all I want to count from 0 to 999. Carefully observe. That means I can have a cascade blocks, right? This is decade counter 1. This is another decade counter. This is another decade counter. This goes from 0 to 9, this particular one, 0 to 9, 0 to 9. Then I can cascade them, right? Is that possible here? Can this particular system work? Just see, 0 to 999 it will come. Will it come from like that? 3 decade counters. Like I can go from 0 to 999. Is that okay? Are there or not?
Yes, ma'am.
Yeah, will it work? So
Yes,
that
ma'am.
means another choice we got that we can have a cascaded mode also, right? So all together, this is units, I mean ones, tens, and hundreds. All together, I can see 3 digits. Don't you think so? That's how we are getting LED displays. This is one counter. This is another counter. This is another counter. All together, I will try to execute. So I can display any number from 0 to 999, isn't it? Yes or not?
Yes, ma'am.
So this is another interesting fact that we can cascade it. Just like your amplifiers in your analog electronics, how we can cascade amplifiers so that we can increase the gain. This is another way, like a decade counter. If we can repeat it, we can do this counting sequences from 0 to 999. I'll add one more. I can do that from 0 to 9999, isn't it?
Yes, ma'am.
Yes, that is one. Okay, so this is another application, right? So another one I will tell you. Another important applications. They have done so many applications. Right. Wait a minute. Some other counters. Okay, just an example. Okay, can you just see this counter? Counter with unused states. We have done this example also. Unused states. That means all the states won't be sequenced. Can you check? There are some unused states. It is a 3-bit counter. Okay, it is starting from 0, 1, then afterwards 2 has come, then 4, then 5, then 6. That's all. That means what is happening? Which are unused there? Which are unused states there? It's not in a continuous sequence. We can skip that, isn't it? Did you observe? It's just an example already worked out. Just check out. 0 to 1 it has gone, 1 to 2 it has gone, then 4, then 5, then 6, isn't it? Or 7? 4 is there, 5 is there, 6. Yes, 3 is not there, 7 is not there. Then also we can design in a synchronous mode. Don't you think? These are unused states are there and then we can do that. Did we do or not? And this sequence can be repeated. This is just a synchronous example I am trying to tell.
Ma'am, only 3 is not there.
7 is also not there, I guess.
5 is there in present state.
Not 5, 7 is not. Yes or not?
Ma'am, please make understand once more.
See, I am trying to design a counter which goes through this sequence. After 6, it will be back to 0. That means it's a synchronous counter. Synchronous, not asynchronous. So present is 0, then it is going to 1. Present is 1, then it is going to a predefined sequence. Then present is 0, it is going to 4, then this is present state, this is next state. You can use how many flip-flops? 3 flip-flops. What type of flip-flops? They have already provided in the question. Use J. So J, K, otherwise J1, K1, J2, K2, J3, K3. That's all. Synchronous. Means I am telling that you need not have a continuous sequence. You can have any random sequence, but it will be repeated. I have done these examples. What is there to explain in that? Counter with unused states. This is a new name, that's all. Did you see? Did we design like this?
Okay, ma'am, got it.
Yeah, we don't have those, that's all. See, it's given here. See, 111 is not used, 011 is not used. But still your diagram will be there. This extra arrows here are not used. But still we have a synchronous counter. We are already designed that. You can use T flip-flop also. We have done with T. They have done with J. Okay, right. Now, a new counter also they have decided. A counter which is called a ring counter. Now, carefully understand. It's a ring counter. Right. So, ring counter is what? What is given there? Statement. Anybody can read? A ring counter which will be a repetitions. Ring counter. Ring counter. Specifically, a register can be used in that. That means we can have a repetition of the values. A ring counter means nothing but a shift register only, and that too is in a circular one. That means what is happening? I will have just a second. Check out. If this is a register having some 3 flip-flops, okay, or 4 flip-flops, right? 1, 2, 3, 4. Right. So this will go to here. This will go, this will go, this will go. Again, this will go, this will go, this will go. So this shift resistor, circular shift resistor, see, whenever it goes, we will collect outputs also. That means I will get different sequences. So they are telling this circular shift resistor as a ring counter. Same name. We have already done this also. A circular shift resistor where we can take the outputs at every point. Then we can get different sequences. Don't you think so? Any doubt in this? Just check out. Just check. A initial value. Don't check the second one. Check the first one. A shift resistor is there. They are using T flip-flops. In fact, I didn't use any flip-flop. I am showing that any flip-flop you can use there. T 0, 1, 2, 3 or D type flip-flops. Anything you can use. And if you collect outputs every time. Every clock pulse, I will collect the outputs. Don't you think I will get one new sequence? See, initially I will keep 0, 0, 0. Right. If I keep 0, 0, 0, what will happen? All the time I will have zeros only. If I use a D flip-flop. If I use a T flip-flop, what will happen? You guys are there or not?
Yes, ma'am.
Yes, ma'am.
It will complement.
Yeah, I am using a T flip-flop and I am initially inputting 0, 0, 0, 0. What will happen? What will be the output?
Output will remain same.
If I use a T type flip-flop, T flip-flop.
After
Ma'am.
first pulse, T dot will.
Ma'am, for 0 it will be same and for 1 it will toggle. Na?
One it will toggle, right? So now question comes, this circular shift resistor, in order to make it work, the initial input conditions is very important, isn't it? Once you input something, like wait, instead of 0, 0, I will keep, and I use D flip-flop, D type. Now what will be the output? First sequence will be 0, 1, 1, 0 only. That is in time t0. First sequence. Time t1, what is happening? Circular shift. No? This one will 0 will come. This will come. This will come. This will come. What is happening? 0, 0, 1, 1. Is it correct?
Yes, ma'am.
Right. In time 2, what is happening? This will come. Right? Now time 3, what will come? Time 4. Time means another trigger time, or maybe I will have different clock pulses sent down. Time 4. Is that correct? So now T5. What I will get? Again a repetition I will get. Yes. Now if you see from here to here, again a repetition is coming. This is first cycle, I can say. Another repetition, second cycle will come. Don't you think so? The sequence. Depending upon the fresh input, we can generate different timing sequences. Now this one, if at all you draw a diagram, how it looks? 0, then 1, then 1, then 0. 0, 1, 1, 0. Then the next one, how it looks? 0, 0, 1. You can do a reference also, doesn't matter. Okay. Then how it looks? This one? 1, 1, 0. It stretches till 0. The start point, just to identify. 1, 1. So now again the repeats. So now this one I will fit to one circuit. This I will fit to another circuit. This I will fit to another circuit. This I will fit to another circuit. Don't you think the 4 different circuits work differently? The generation of time sequence is just like your multi-vibrator. Don't you think so? Is that correct or not?
Yes, ma'am.
This is what I was telling. So this ring counter, depending upon, see, again if I say, I will not say this is the ring counter. I can say this is a circular shift resistor. That's also same meaning. It does generate different sequences. Okay, now, after this ring counter has been identified, right? There is one particular fellow who told that his name is Johnson. Okay, so he told that a different logic. Okay, now I will not explain the logic, just read this one. What he did, he told something different. Generate the timing signals with a combination of shift resistor and a decoder. What he did, he told use a shift resistor, apart from that use a decoder also, then you can generate a different sequences. Just try to read the slide. You people also can propose new ones, no problem. The combinations, that's all. Generate timing signals, like we are generating signals, right? Like this, different one. So a combination of a decoder and this one. So what great things is happening with a decoder and this? So he is telling in this one, what? The number of states can be doubled with things if the shift resistor is connected as a switch tail ring counter. Now what is a switch tail ring counter? We have to first identify, isn't it? Now let's get back to the old one. Right, here I told not to see. Now see, that is what he proposed. What he told, a combination of a 2-bit counter with a 2x4 decoder. So this is, he is telling that you can double the sequences. Now let's see how correct he is. Now is it working like this? Just check. A combination of a decoder and a combination of this. What is new about this one? What is new about this? There is a shift happening, definitely. Okay, the last one is coming. Which was the last one? E dash is coming here. Did you understand anything here? Saying this is what Johnson has proposed. Yes, you guys are there or not?
Yes, ma'am.
What did you understand from that? A sequence number is given. Okay, that is continuous for 1, 2, 3, 4, 5, 6, 7, 8 they have given. And now you see. What is the first one is 0, 0, 0, 0 they have input. Then afterwards what is happening there? What is A dash, E dash, then A B dash, then B C dash? What is happening there? Anything you understood from this? 2-bit counter outputs are there, no? They are passed through the decoder. Now decoder 2 input means 4 outputs you will get, na? Take this example.
Yes.
Yeah, see, first a 2-bit counter is designed. Okay, right? This outputs every time they are passing through a decoder. That means I'll get 4 states, 4 outputs. This is what Johnson has proposed. From a 2-bit, I can generate this bigger sequences. Is that happening? Is that happening? Is that happening or not? No? Guys are there or not?
Yes, ma'am. Yes.
How? See, earlier when shift resistor is used with a multiplexer, you got a universal shift resistor. Now, a shift resistor on a counter, along with a decoder, we are increasing the sequences. Is that happening? Now, what great thing happened here? Tell me. See, if at all you use a 2-bit counter, this example I am telling you. Please try to understand. Previous example. Here in this example, how many flip-flops I have used? Hello? Guys are there?
4.
4.
Four.
So how many different signals I have generated? See, after this it's a repetition. Okay, how many different signals I could generate? 4 different signals. 4 flip-flops, 4 different signals. Isn't it?
Yes, ma'am.
Okay. Now, this Johnson fellow, what he did? He used 2-bit counter. That means he used 2 flip-flops. Right? A 2 flip-flops connected to a decoder, he generated 4 sequences. Don't you think so? He has literally made the number of flip-flops usage very less, half. Check out. This also 4 sequences. Ultimately, here also 4 sequences. See, after passing through the decoder, you will get a sequence 1, 2, 3, 4. Here also 2-bit counter again specified. Don't you think so? This is what his proposition. Use a counter and in fact pass it through a decoder and generate a sequences. Are you able to get? Switch the tail of that and then connect it. That is what he was telling. But anyway, the hardware implementation is as tedious as the normal one. Why? Because the decoder has to be designed, no? Isn't it?
Yes, ma'am.
Yeah. So now please try to understand how the Johnson has constructed. Are you getting any ideas? Like, can we make it a more different? So we will have your 2021
There are
batch.
four.
Yeah. See, if there are 4 flip-flops, they are having 8 sequences now. So that means with 4 flip-flops, I can generate 8 sequences. Whereas in your ring counter, with 4 flip-flops, I can generate only 4 sequences. Isn't it?
Yes, ma'am.
Yeah, that is what Johnson has told. Don't just fool away Johnson. Okay, so Johnson counter is again a very good question. In fact, you can check out all the counters at a stretch. Okay, we have studied basically in a bigger form, synchronous, asynchronous. Right. Again, there are some small additions such as ring counter, a ripple counter, right? Then afterwards, switch to end-tail counters. So everything is a small differences, small changes, right? Nothing much. Design aspects are not more. Only a reutilization in a different combination of different mixture of combinational circuit and sequential circuit, isn't it? So till now here, whatever I have taught you guys is applications of flip-flops. Right. So you people clearly go through this because tomorrow class, whatever I am going to teach, that is state machines, is a completely new one. Okay, it's very tough also. Tough in the sense, if you don't follow my class. If you read it will become very difficult. State machines are very interesting if you follow the class, right? All of a sudden, don't think like, okay, from where to where we have moved. That also is a design only. So till here is one level. From state machines, it's another level. Got it? So tomorrow is, when is my class? Shweta?
Yes, ma'am. Hello.
Yes, tomorrow when is my class?
1:15.
1:15. Okay, so don't miss tomorrow's class. State machines classes, I will tell you. I'll start that one. So till here, I'm planning to give some assignment, right? Whether you submit or don't submit, it's not mandatory, but you practice. Okay, some 30 to 50 questions I will frame. Is that fine? You can practice.
Yes, ma'am.
Okay, all
Yes,
from
ma'am.
the start to the end, all the questions. I told them my students just to type it. So afterwards, you just practice. I will assort all the questions, right? Don't try to cheat or anything. No, because I'm not asking any submission. But you practice. Is that fine?
Ma'am,
Yes, ma'am.
Yes.
ma'am, can we get this slide?
Oh, this line. Yeah, yeah. I'll post. I'll post. I'll do it.
Thank
I'll give it. Okay, I'll do it. Okay, I'll share it. Okay. So now, so tomorrow class we will meet then.